So, in previous lecture, we have seen that how can we sort elements using heap sort. Is it better than other sorts? No, it is not better than other sorts. It's not better than merge sort and quick sort. Then why we have done heap sort? I've already told you. There are some operations that can be performed faster on heaps, like insertion. Then there are operations like find min and extract min. Those operations could be done better in heap sort. And the other sorting techniques like merge sort and quick sort are. So heap sort is not better than merge sort and quick sort. In some cases, some applications are better in case of heaps. That's why we have studied the another sorting technique, that is heap sort. Now let's discuss its complexity. So the complexity is actually n log n in best case as well as in worst case. It is n log n, same as of those two, but it is in the best case, or whether it is the worst case, it is n log n. But if we take large number of elements, the complexity of implementation will increase. So that's why we use quick sort or merge sort in case of sorting in analog and time. Okay. So what is the complexity of making a heap? First, we want to know what is the complexity of making a heap. So let's say this is a heap. This is actually a heap. This is a complete binary tree with how many nodes? There are, I suppose, 15 nodes. There are 15 nodes, and I have told you how to calculate number of nodes in a tree of height h. Okay, so we can calculate the number of nodes, but uh, now in order to make the heap, what I'll do, what I'll do, uh, we'll take the worst case actually. What is the worst case? Worst case is we even making these leaf nodes, we are making these leaf nodes also a heap, max heap. In case of max heap, we are making these leaf nodes also max heap. Otherwise, in our algorithm, what we have done, we have started from the first known leaf node and make it a heap. Then second known leaf node, then make it a heap. Then we have moved forward and so on. We'll keep on going, and this whole will become a heap. Okay, but now consider it is the worst case that we also want to make these nodes, leaf nodes, also a heap. Okay, in that case, what will happen? What will happen? The max heap will not always be applied from root. So if we want to count max heapify, it will always not count from root. So we cannot say its complexity is its complexity is log n. We cannot say that because height of tree is log n. So it is not always applied on from the root node. It is not always. It is not necessary. It could be applied from this, and that's it. Then we do not require the leaf node. So the work done at every level will be different. At this level, work done will be more. At this level, work done will be more. At this level, work done will be less. Sorry, at this level, it's more. It's lesser than this level. It's lesser than this level. So it depends on number of levels in the tree. So how many nodes are there? So it depends on number of nodes. How many nodes are there? So how to calculate that? So we can calculate that with the help of at particular levels. How many nodes are there at a particular level? Let's say this at this level, how many nodes are there? There are 8 nodes. How can we calculate that? So there is a formula for that. So we need to, because understand this again. Work done at this level will be more. Work done at this level will be less than this. Work done at this level will be lesser than this, and work done will be in order to make all these elements a heap, max heap. In order to make all these elements a max heap, so time taken will be more. In order to make only these elements heap, time taken will be lesser than time taken at this level. time taken at this level will be lesser than time taken at this level because number of nodes are less. So how can we find number of nodes at particular level? Only at this level, that is a zero height. Okay, at zero height, and this is height 1. I have told you how to calculate the height. Height is nothing but number of edges. So there is no there are no children, more children here. So height is no edges there. So height is 0. Then height is 1 because only one edge. Then height is 2 at this level. Height is 3 at this level. So work done at particular level will be more than the upper level. So that's why we need to find out what will be the work done at particular level. At one level. At one level, the work done will be 2 raised to power h plus 1, and its seal value. It's not the flow value. If answer will be like 3.5, so we can say it is 4. So that is the seal value. Now we can check the formula if it is giving us the right answer. So it is nothing but n divided by 2 raised to power h plus 1. 2 raised to power h plus 1. So it's flow, it's seal value. It's seal value. What is n here? N is number of nodes in tree. Total number of nodes. Total number of nodes in that particular tree. What is h here? H is height at that level. So this is number of nodes. This formula is for number of nodes at particular level. At particular level. Number of nodes at particular level. Let's say I want to find out what will be the number of nodes at 0 level. So I can see that 8. How can we tell that to compiler? So with the help of formula. Okay. So how can we calculate that? Height is what is h here? H is the level of the tree. So in this case it will be 0. Okay. And number of nodes, total number of nodes are 15. So what is the formula here? 15 divided by 2 raised to power 0 plus 1 and its floor value. So 2 raised to power 0 plus 1 is nothing but 2, and the answer will be 15 divided by 2, that is 7.5, because we are taking its seal value, sealing value, that is 8. So number of nodes at 0 height is are 8. Okay. We can also check the other. So at one level. So if we want to check the number of nodes at level 1, that will be 15 divided by 2 raised to power 1 plus 1. 2 raised to power 1 plus 1, and it will be nothing but 2 raised to power 2, that is 4. So 15 divided by 4 is 3 point something, and it will eventually will become 4. So there are 4 nodes at one level. Then we can check it at 2 level, and then we can check it at level 3. So number of nodes at particular level are this many. Let me write it again. How many number of nodes are there? So are this many. N total number of nodes, and the formula is for nodes at particular level. So that is 2 raised to power h plus 1. H is the height of that particular node. H is the height of that particular node. So at one node, at one level, this many nodes will be there. This many nodes will be there. And how many times do I have to do this? Order of h. Work done at this level plus work done at this level plus work done at this level plus work done at this level. So that depends on height of tree, order of h. Order of h. So that is the complexity. We need to solve this one. We need to find out the exact solution. So again, A max heap will not always apply from the root. That's why we need to find out if there are 8 nodes here, work done here will be more. 4 nodes are here, work done here will be less, and so on. So at particular node, the work done will be different. That depends upon height of tree. So this is how to calculate number of nodes, and this is that it will depend upon height of tree. Okay. Now let's see how can we solve this one. How can we solve this one? This is just pure mathematics, nothing else in it. I'm going to write it again. It's just a discrete maths. So let's find it out. How can we solve it? So can I write this? N by 2 raised to power h plus 1 and the seal value of 8 and order of h, big O of h, and the height of tree could range from 0 to log n, 0 to log n, because log n is the maximum height of tree and it starts from the 0 height. We have just seen that if the last leaf node will have height 0, okay, then 1, then 2. We have just seen that. Okay, so it will start from 0 to log n. Maximum height is log n of a tree. Now at particular level, it will be taken because what we have done here, why we have taken order of h, it is nothing but constant of c. Some constant time will be taken here, and we have ignored the constant and marked the height as order of h. Now in order, we cannot solve order of h here inside this summation. So instead of writing order of c, I'll go back to one step and write some constant time will be taken here. So I'll write here n by 2 raised to power h plus 1 and c of h, some constant time will be taken. Okay, and then again it varies from h varies from 0 to h varies from 0 to log n. Now I can also write this h plus 1 as 2 raised to power h dot 2 power 1. This is the same thing. So 2 raised to power h plus 1 and this one is same thing. Now what I'll do, I'll take all the constants out of it, because we need to ignore all the constants in order to find the complexity. In order to find the complexity, we need to ignore this one. So what are the constants? C will be taken out, 2 raised to power 1 will be taken out, and we'll write here h equals to 0 to log n, and here we can write n by 2 raised to power h. N by 2 raised to power h, and it is n is also constant. We know number of nodes. So n, c and n will be written here, and h will be here. H will be here. Okay. So n is the constant. So we need to solve h. In order to solve this thing, we know that this is the maximum limit. But what if I can take it to the infinity? I can take in order to solve this problem. So I can also write this is less than or equals to what is the worst case? Worst case is that height could raise to infinity. Height could get raised to infinity. So in order to do that, I can simply write that this equation is less than this equation. Okay. So this equation is less than this equation. What is this equation? This one is to the infinity, and only difference is here we have log n. Log n is the maximum height of tree, but there is no harm in taking that the height will get raised to infinity, because we can solve this one. What is the answer of this one? There is the answer for this one. This is a harmonic progression, and the answer of this only term is 2. So we can write Cn by 2 into 2. So our complexity will be order of n. Order of n. In order of n time, we can make any array a heap. So in order of n time, we can make any array a heap. So in order to this is the complexity to make a heap. But what is the complexity to make to do a insertion sort? So for every element, for how much time do we need? This can be seen here. So what are we doing? We are making a heap in order of n time. We are making this a heap in order maximum. That is the worst case. Order of n time. Okay. If we take the best time, then also it will take order of n time, because that many comparisons will be done. But this is to make a heap. After making heap, we want to do insertion, the heap sort. That is, if there is the maximum element at the top, we want to get it down here. So it will have to travel all the nodes here, all the nodes to the bottom. So that, and again we have to apply the TP5 procedure again from the height of tree, that is log n. So log n, and it will be done n number of elements time, n number of elements time. So the complexity is n log n in case of whether it is a best case or it is a worst case. So if we do not make any difference between the number of elements, whether they are sorted or not, then we have to make it a heap. And in order to make it a heap, it will take order of n time. And after doing the sorting, so how can we do a sorting again? Let's see that if this is the example, this is the example. Let's say so. This is the example, and this is our array, and how much time will be taken to make it a heap? It will be taken order of n time. And after making it a heap, after we have made this a heap, so this will be like this. And if there are more elements, then this will be like this. Okay, anything will be like this. Now what we are going to do, we are going to pick this last element and copy it here, and 3 will come here and 15 will come here. This is one time that we have used it. So 15 will come here. And if 15 is coming here, all the other elements, on all the other elements, I'll apply the heapify procedure again. I'll make all the other elements heap again, but will exclude this one, the last element. Okay. In the next pass, what will happen? The second highest element, that is 5 in this case, 5 will come here and will exclude these two elements and make all other elements a max heap. And we'll keep on doing this n times. So in order to travel from the height to the bottom, in order to travel from height to the bottom, it will take log n time, and this have to be done n times because there are n elements. Okay, n minus 1 elements, because for first element, that always last element, it will be sorted automatically. So the complexity is n log n. Okay, this is the complexity of heap sort. Let's start our new topic, that is counting sort. And what is a counting sort? It is a sorting technique, same technique, but there will be no comparison in this technique. There will be no comparison in this technique. That's why it's faster than the other techniques. But there are some limitations of this sorting technique. We'll discuss limitations and advantages of this counting sort. First, we shall see what is counting sort. Let's see that. Counting sort is a sorting technique based on keys between a specific range. So that is actually the advantage as well as the limitation of counting sort. It works by counting the number of objects having distinct key values, then doing some arithmetic to calculate the position of each object in output sequence. So counting sort is done in this way. So what will happen? We'll see the procedure. What is written here? We'll see that. For simplicity, consider a data in range of 0 to 9. Okay. Otherwise, what will take? We can take the maximum element out of this array and will create a temporary array of that size. Or you can simply create, because we know all the digits will be from 0 to 9, and then all the digits are from 0 to 9, so that much will be the size of temporary array from 0 to 9. Let's consider that. So create a count array to store the count of each unique object. What we are going to do is we are going to count the frequency of each element. Like here, 1 is occurring 2 times, 2 is occurring 2 times, 4, 7, and 5 are occurring only 1 time. Okay, so that we are going to do here. Let's see that. We have created a temporary array from size 0 to n. And initially, we'll put all the elements as 0. Initially, we will put all the elements as 0 inside this temporary array. And then place the count. So 1 is occurring 1 time. So I'll increment the position index of 1 with 1. Okay, not the index, but the element at that index. Initially it was 0. Now, after counting this thing, this first element, that is 1, we have incremented 0 by 1. Okay, then 4. At fourth position of this temporary array, will increment by 1. This means that we have encountered 4 one time. Then again we have encountered 4. So we'll go back to this index 1 and will increment the element at this index, that will be 2 now. Okay, then we have 2. So we'll go to the temporary array of 2 index and increase that element from 0 to 1. And then we have 7 and we'll increment 0 to 1. Then we have 5. We'll go to this 5 index and increase it by 1. And then we have 2 again. So 2 was 1 earlier, and we'll override this value of 1 by incrementing it by 1. Okay, so that is 2 again. Now, what is the next step? Modify the count array by adding the previous count. So we want to find out the maximum count. So what I'll do, I'll add these two terms and store the value here. So 0 plus 2 is 2, I'll store 2 here. 2 plus 2 is 4, I'll store 4 here. You can see that in the animation. So 2 plus 2 is 4. 4 plus 0 is 4. Then 4 plus 1 is 5. Then 5 plus 1 is 6. 6 plus 0 is 6. Then 6 plus 1 is 7. 7 will be stored here. 7 plus 0 is 7. And then we have 7 plus 0, that is 7. Okay. Now what is the next step? Since we have 7 inputs, we create an array with the 7 places. One more array will be created. See, I've told you that there is a trade-off between space and time complexity. If time becomes faster, it means order of n time. We can do this sorting in linear time, that is n time. order of n time, not n square, not n log n, but only in n time, like we did in the searching. So what will happen here? We have taken two more arrays. So space is increasing and time is decreasing. So time is getting better, but space is getting worse. So that is the space-time trade-off. So 7 input array will be taken, one more array will be taken here. And in that array, what we'll do, see it very carefully, we'll place the objects in the correct position and decrease the count by 1. We'll place the objects in their correct position and decrease the count by 1. So we'll start with this our input array, that is 1. The first element is 1. At one position we have element 2, and we will place this 2, this 1. Hold on. Let me show you that again. So one element is there, we'll go to one index, and 2 is there. At 2 index of this output, we will consider this this element as index of this new array. So at 2 position we will place 1 and decrease it by 1. See it. Okay. So now the next element is 4 in our input array. At 4 position there is 5. We'll go to 5 index, and there we will put 4 and decrease here by 1. The next element is 1 again. We'll go to the 1 index, and there we have 1. So we'll put 1 at 1 index. 1 at 1 index and decrease it by 1. It means there is no other 1 left now. It means there is no other 1 left in this array. So we have placed these two ones at its correct positions. Now next element is 2. We'll go to 2 index. There we have 4 as an element, but in output array we'll consider this 4 as a index. So what is index here? 4. At 4 we will place this 2 element. So element 2 is placed here at 4 index. Okay, and we'll decrease it by 1 again. And here we'll have 3 now. Now we have 7, and 7 is at 7 index, so we'll put 7 at index 7 and decrease it by 1. Then we have 5. 5 is at 6 index, so we'll put 5 at index 6 in the output array and decrease it by 1. And at last we have element 2. We'll go to 2 index. There we have element 3, and at 3 index of this output array, we'll place this element 2. So 2 is the element here, and we'll decrement it by 1. Okay. Now we have finished with the array. Our array is sorted now. You can see that our array is sorted. So this is counting sort technique. So this is our sorted array that we can see. Now we will see its code actually. Let's see that. We'll understand its code. Now I'll explain the main portion. So this is how we count the frequency. This is how we count the frequency. How it will work, let's see that. This is plus plus count. Count is also an array which is initialized with 0. So there is again one more array, that is our initial array, and it is being used as index. Its element is used as index. Let's see that on the board, how it will work, how it will count. So I'm sharing it, and now you can see the code. Let's see the example on the board. So if these are the elements 1, 2, 5, 7, 4, 2. Let's say these are the elements. Now this is our array ARR, and there is our count array, which is initialized with 0 from 0 to 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And one more element we need 0. Okay. So all these elements are initially 0. How can we count the frequency? What we are doing here, we are writing it plus plus count. Count is name of this array. Okay, and this array's name is ARR. And we are writing here ARR of I. So what will happen? We'll apply a loop here from 0 to number of elements. So let's say A of 0 is what? A of 0 is what? 1. So A of 0 is 1. And now index 1 will get incremented of count. Of count, we will increment index 1. That is 1 here. So 1 will get increment. That is so simple. So if it will increment by 1 again, so that is 2. So A of 0 and 1. That this will become 1, I will become 1. But at A of 1, we have 2. So 2 will become the position of count array. 2 is the position of count array and will increment at that position. So that will become 1. So this is how it works. So it will check all the elements and increment it one by one. If the element get repeated like here 1. So let's say if the index is 2 now. So A of 2 we have 1. So we'll write here 1. So count of 1 will again get incremented by 1. So it was 1 earlier. Now we'll make it 2. So this is how we count the frequency of any number. Okay. So that is being done in the program. So first we'll count the frequency and then we'll find out the total of that number. Let's see that again. So here, what is the next step? First, we are counting it, and then what is the next step? The next step will start it from 1. We'll not count the 0th element, but we will start adding it from 1 because at this index we are counting the addition. So what we are doing here is count of I plus equals to count of I minus 1. So we are adding the current element with the previous element that we have seen here. Let me open that. So we have just seen this thing. So 1 and 0 will be added. That will be 2 because there is no element, no such element that is directly 2. That's why it's not shown in the animation. And then this current element and the previous element, count of I and count of I minus 1 will be added and stored in count of I. That is written here in the code. That is written here in the code here. Count of I equals to count of I plus count of I minus 1. So that is being done in this way. Now the next step, it modifies it into the sum count. Then we place the object as it is at its correct position and decrease the count by 1. So decreasing count is being done here. Just like we have increased the count, we have written plus count A of I. And similarly, we have written minus count A of I. So the value will get decreased, but how it will go to its correct position, that is written here. We have taken one more array, that is output array in the bottom, and then we'll write this thing, count of A of I minus, because we are starting from 0, that's why we have written 1 and we'll store that element in this thing. Let's see how it is working in this our example. And at last, what we can do is we can copy this output array to our original array, and we can display it later. So this is how we do the counting sort. Let's see this one, count output of count ARRI minus 1 equals to ARR. So let's see that with the help of example. Okay. Um, okay, let me open the example for you again, and here you can see we have the addition array. Now what is the next step? You can see the screen as well as the PPT. So what will happen in this case? So this is our count sum array that you can see on the screen, that is 0, 2, and then 4, 4, 5, and 6, 6, and 3 sevens. So this is our sum count that we just did in the previous step. So these are the indexes are very important in this, and this is our original array 1, 4, 1, and that is 2, 7, 5, and 2. This is our original array, and the indexes are, let's say it's our these are 0, 1, 2, 3, 4, 5, 6. Okay, and there is one output array, this one, that is having 7 elements. Okay, this is having 7 elements. Now what will happen? What is written there to put the element from this position to here? So what we will do here, will start from this one. So this element, we will check the index here 1, and it is at 2 position. So we'll check the index of this output array. So what we have to do here, at output array and of count array, this is count array, and this is ARR, our input array. Now this array's element should be considered as index of output array. So we want to make this element as the index. So how can we do that? By putting this square bracket. So we'll write here count. Okay. Now whatever element is there in this array will be considered as index of this count array. So again I'll write here count ARR of I. And if we are doing it for starting from 0, then we can subtract 1 from it. And after doing that, we'll put ARR of I in it. So that is what we have done. Understand this again. What we have done here, the element at this array, ARR should become index of count array. So count array is index. How can we make it? By putting square brackets. Then count of this array minus 1 will become index. So this 2 will become index. So we don't want to store it at 2 position. We want to store it at 1 position. That's why we are subtracting 1, because index is starting from 0. If it is not starting from 0, then need not to do minus 1. Then we can place it here and here. So 1 will get placed here and here. So this is how it is done. Let's check it. So it will start with the I of 0. So A of I, then A of I A of I, that is 0, will return as a element 1. So counts 1. What is the value of count 1? That is 2. So 2 will become the value of count. Now we'll subtract minus 1 out of it. That is 1. So at outputs 1 position, we will store what element? A of 0. That is 1. So we'll store 1 here. Okay. And decrease and reduce it by 1. So it will keep on doing until our array is finished. So that is how it is done. So that is our counting sort. As we can see from the example only and from this program, there are no two loops in it. There are no two loops in it. In loop inside it, there is no nested loop in it. So the complexity will be n plus n plus n. It could be n plus k, but constants can be ignored. So this is done in a linear time. Only n time will be taken to sort elements using counting sort. That's it about counting sort. We'll discuss the next sorting technique now. So let's see radix sort now. What is radix sort? So let's see that. The algorithm is only used to sort numbers. So we cannot sort alphabets or strings with it. We sort numbers from least significant digit to the most significant digit. So first we'll consider the least significant digit and then we'll go towards the most significant digit. We use counting sort as a subroutine to sort, like we did in heap sort. We have called heapify and build max heap. In a similar way, we will call counting sort in the radix sort. So counting sort we have already understood, and now we will see how the radix sort will work. So it is very easy technique. So let's see its example. Consider this input. These are the elements 70, 45, 75, 90, and then 802, 24, 2, and 66. Okay. So these are the elements. First, consider the ones place. So we need to sort the ones place first. Okay. So counting sort will be applied on only the ones place. Okay. So we are using counting sort to sort ones place actually. So we can see these are the all ones place number. So this 90 and 70 have same ones place number, that is 0. But 70 is coming first, so we'll write 70 first, and then 90. Then we have 2. There are two 2's on the ones place, that is 802 and 2. So 2. This 802 is coming first, so we'll write 802 first, and then we will write 80. Then we'll write only 2, and then we have 4 and 24 will be written here. Then we have 5 in 45 and 75. So 45 will be written first, then 75, and then 66. So this is the first step. Now observe, this is written here. The observe that 70 has come before 90, and this is because it appeared before in the original list. Next step is to sort the elements at tens place. The same counting sort will be applied again. And after sorting, we can see that these are the elements. And at last, we need to see the elements at hundreds place. So ones place, then tens place, then hundreds place. So there are all 0 elements here. And there is one this. So we can see 2 is occurring first, and 2 is at 2 is having 0 as a 100 place. So 2 will come first, then this 2 will come first, then this will come first, then this will come first, and then we have 75 with 0. 75 will come first. 90 with 0. 90 will come first, and then we have 170 and 800. So our elements will be sorted. So the elements are sorted, and let's see its code. So what will be its code? So very simple code. This is just the code of radix sort. Okay. Find the maximum number to know the number of digits. So in our case, the maximum number was 302 or 308. So we need to find the maximum number so that we can count the number of loops. So how many number of loops will be there? Number of iterations. Number of iterations will be how many digits are there in the maximum number. In 802 there are 3 digits, so this loop will work 3 times. So 3 times this will be called, and at every time we will take the last index, last digit of the element. What we'll do, we'll divide this maximum number by 1, then we'll get greater than number 0, and it will increment by 10. Let's see that on the board. And one more thing, let me make it clear to you. Okay, then let's see that. Hold on. So let's see this example of radix sort. How many times actually the number of iterations we need to count, the number of iterations, that how many times. Uh, we know that already in our case it will run 3 times. Okay, it will run for 3 times. So what is the loop written here? That is, it will start from 1, and then it will go to m. M is the maximum number. Okay, divide by this exp that should be greater than 0. Division should be greater. This is the exit condition of the loop. And then we have this, that we want to multiply this with 10. Why we have done this, I will tell you just now. So see this, it is equals to 10, multiply equals to 10. This means exponential equals to exponential into 10. Okay, so we have passed exponential to the counting sort. So counting sort will do the rest. But in that also, that is not mentioned in our program. We will divide it. We will take a mode of this number with 10. Then only we will able to find the element at the unit digit, and then we'll apply the counting sort on that unit digit. So everything will be done in this case, in counting sort. Okay, but how this will run 3 times, because we know our maximum element is of size 3, that is 802. Let's, okay, 802. Now it starts from 1 and we'll divide it with 1. So once we divide this 802 with 1, what will be the answer? What will be the answer? So 1802. So value will be 802 here. Okay, 802 will be here. So this is greater than 0. This loop will work. But what is the next step then? What is the next step? We need to multiply this with 10. So now earlier it was 1. Now it will be 10 in next time. Once we are done sorting the elements at unit place, we'll deal with the elements at tens place. So this is our element, and if we divide it with 10, we'll write 80 here, and this will be our answer. And 80 is greater than 0, that is true, and we'll pass 10 to the exponential. Okay, we'll pass 10 to the exponential, and whatever our number is, now we'll pass this thing to our array, that is counting sort, this thing 80. So 80 will be passed. So 80's mode will be taken here, and second element we can fetch from the number. After that, again, this number will be divided, but the exponential is multiplied with 10 now. So it will be 100 now. So 100 divided by 802 will be 8. So this number will be passed to the counting sort. And we have a remainder here, 0, and this number will be passed. So we'll reach to the number at hundreds place. So that's it. That is how it is done. We'll see its elaboration in the lab part and its programming. We'll see how it is done and we'll see its elaboration. So that is our radix sort. So that will be all for today. And we'll start with bucket sort in next class.